Welcome to the Global Composite Expert webinar series hosted by CDM Hub. This webinar series is to examine the history, present capability, and future of composites, with the goal of sharing the vast knowledge of composites that has been developed over the past several decades. This webinar series is initiated by the leadership of Composite Manufacturing Simulation Center at Purdue University. We are located in this beautiful building called the Indiana Manufacturing Institute. When life returns to normal, we hope to welcome you to visit us. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. The CDM Hub provides a very powerful website called cdmhub.org for the community to collaborate and carry out this mission together. And we envision CDM Hub to be the premier resource for composite design and manufacturing. And this webinar series is one of the initiatives CDM Hub started as a service to the global composite community. This webinar series are made available by the support of CDM Hub's sponsors, including Dassault Systems, Cytec Solvay Group, MSC Software, through Digimat, Modex 3D. We greatly appreciate their generosity and also contribution to CDM Hub. They invite more organizations to join them and join us to support CDM Hub's mission of convening and serving the global composite community. This webinar will be recorded and made available on CDM Hub, and an email will be sent to all attendees once the recorded video is available. And the presentation will last around 40 to 45 minutes and will have about 15 minutes for questions and answers. All attendees will be muted. Please submit your questions through the Q&A box. Next, I will ask Dr. Byron Pipes to introduce our distinguished speaker today.
Thank you, Dr. Yu. I'm delighted to be here today this morning to share these ideas with you and to introduce our speaker, Dr. Kenneth Reifsnider. He's the director of the Institute for Predictive Methodology and the Pratt & Whitney Professor of Design and Reliability and Mechanical Engineering and Aerospace Engineering at the University of Texas Arlington Research Institute. The primary focus of his current research is the effect of changes in material properties on long-term performance of material systems and the pursuit of representations of localized material state changes as inputs to multi-physics models that predict how such material systems perform in relationship to micro and nano detail of how they are made and the manner in which they are used in engineering devices and systems. Applications of the results of this work relate to durability, reliability, virtual design, and system science relationships. In 2004, Professor Reifsnider was elected to the highest honor of the engineering profession, the National Academy of Engineering. The citation read, "For the development of strength-life relationships in composite materials and structures." We're delighted that Professor Reifsnider has accepted our invitation to share his ideas in this area of this current research as a lecturer in the Global Composites Expert Seminar Series of the Composites Manufacturing Simulation Center. Dr. Reifsnider.
Thank you, Professor Pipes, for that generous introduction. And it brings several of the words I'd like to emphasize during my discussion to life, and I'll try to expand upon those as we progress. Defect coupling is the beginning of my title, and we'll see why that's important in relating what we have learned about damage development and progression in composite laminates and strength and life, which has been a lifelong objective of my work in this field. Let's concentrate on the left-hand column here. You heard the word performance, and I'd like to emphasize that for several reasons that'll become obvious as we go along. Performance looking at the bottom, is based on operational observables and knowledge-based models to reduce the development and maintenance cost, time to market, and risk. The objective is for us to develop first principles models that allow us to predict the performance that our part was designed for and manufactured for. So this is somewhat different than just learning about the defects that develop. We want to actually predict strength and life from first principles. Now, this has been correlated with some change in the field, as we'll see later on from the certification standpoint, which has moved from prescriptive, how long can a crack be, what is this delamination, to a descriptive, which says, will this thing fly? Will it get you there? Will it get you back? Performance is a data and risk-based system analysis and control, which is what the certification is requiring. Here are the people that are involved in this work and have done most of it. This chap at the top left, Endel Jarve, has been working in progressive damage analysis for most of his life and is known around the world, I think, in this field. And his analytical models of local defect development and growth are widely used, especially in the Air Force and by NASA, and by quite a number of industries, including several of our local industries. Lockheed is one of those industries. Bell is another one, and so on. So the industrial people, as well as the agencies, are interested in this business of trying to predict computational modeling, develop computational model to predict the onset, the growth, and indeed the combining of defects and materials. Professor Jarve has worked in that field quite a lot. Bottom left, Russell Ryan. The properties and performance of materials in the laboratory, experimentally, how to determine those is his responsibility in our group. And he's also an expert in bonding. And we have done quite a bit in that field fairly recently. And Professor Ryan is involved in leading that work. Top right is this fellow, Reifsnider, who's worked in predictive methodologies and performance for quite a long time in composites. Bottom right is Vamsi Vodlamudi. When we get to this business of coupling, actually modeling, multi-physics modeling of coupling of defects to cause fracture plane development and therefore determine strength and life, we will be talking for the most part about Vamsi Vodlamudi's work. The work for the two folks in the center will not be discussed today. One is sensors. We do have a lot of activity in that, as you might expect, try to get information out of the material during service. And finally, in the bottom center, Yia Zhao is involved in mesoscale phase field simulations, mostly in electronic materials, which of course controls their functionality. Well, here are some of the materials we're going to be concerned with. And you, first of all, can clearly see they're all composite materials. Most of our discussion will center on this diagram in the center, which is indeed a fibrous composite out of a wing structure. This happens to be out of an airplane. And you can see the fibers clearly in these materials, this fibrous composite laminate. They are in different directions, of course, multiaxial laminate. The fibers are aligned, and of course, we, in our models, assume they are aligned perfectly. You can clearly see they are not. They are not spaced exactly the same everywhere. And this material is extremely heterogeneous at the local level as well as at the laminate level. And of course, that affects our global description. We will also, not in this lecture, but we've also applied these methods to the composite hip stem, item C in the center of your screen. And that has various advantages. We can adjust the stiffness to match the bone, very different than the metallic ones, and widely better in various cases, almost every case. This hip stem is now quite popular in Europe. We will not be talking about multifunctional materials, as you see on the right-hand column, the mesophase materials. They are fuel cells. This is an incredible fun field. It involves not only mechanics, but it involves electrochemistry. It involves transport of fuels in and excess stuff out. And as I said, it involves generating a current. Fuel cells now are widely used on trucks that go across continents in Europe and the United States. And use hydrogen, which is quote unquote a fuel of the future. We won't talk about the biological side, but it's quite vast. The composite world in the area of artificial proteins and things that get inserted into the blood is extensive. We have a little activity in that, but not as much as we would like, but it's a growing field. So I needed to make sure we mentioned it. So what is our premise? We're speaking about defect coupling. Why is that? We've spent, in my case, almost 30 years with careful experimentation to follow discrete damage development. When does a crack form? When do several cracks form? When does a delamination form? How do they relate to each other? All of this at the local level. And some of these analysis, the progressive damage analysis codes now are extremely capable, including nonlinear local behavior and the elimination of nodes from a finite element grid, which is quite a task. The loss of strength or loss of performance in our case, and the sudden death that we frequently observe in these materials is controlled by defect coupling. When do these things combine, and how do they combine to tell us how long it's going to last, or tell us if the airplane is going to get where it's supposed to go or not? So we believe that some of the recent advances, especially in analysis and experiment, have put us on the threshold of understanding that last phase, this business of coupling and predicting final strength in life. And we'd like to try to talk about that subject today. So the topics we're going to address, first of all, the classical information and progress that everyone has made, you're hearing about on this series, the initiation, growth, and coupling of different stages of loading of the defects inside. Then we're going to introduce, in order to address coupling, the concept of dielectric permittivity. Now, for everyone in the plastics area, and especially in the insulation area, and this is a familiar property. As a matter of fact, it's used in manufacturing to follow the progress of solidification of many polymer materials. Polymers are poor conductors, they are used as insulators in many cases, but they do have the capability to polarize. For charge to develop inside the material, maybe distribution of electrons, and to align that charge as a function of the applied voltage across these materials. It turns out that that process of polarization is extremely sensitive to internal defects and how they relate to one another, as you might guess. So we'll look at that. Try to simulate those, third item, and then, of course, summary and conclusions, and talk a little bit about what we don't know, which is, of course, much more than we do know. Now, I suspect that by now, many people who are watching and have seen these diagrams because they've been used the world over for a very long time. It is our imagination of the damage development as a fraction of life on the left-hand side, normalized fraction of life. And you can see this sweeping curve, bottom left to top right, which indicates damage develops at the beginning of life, micro cracking typically, matrix cracking. Then things level off quite a bit, and then there's this acceleration at the end. And we're going to discover that this is a two-step process at the end, not a single one as we thought, or at least I thought. Anyway, this remaining strength going out, it's okay, well, it's not quite okay, and then it's really not okay, it fails rather quickly. This sudden death that develops at the end is controlled by defect coupling, and another detail that we'll introduce subsequent to that. The diagrams that we've been drawing for years that we think look like what we should see in the laboratory are the ones on the right-hand side. And you can see that cracks start out, then they somehow find one another, and then they go through the thickness and they cause failure. We really didn't know what that chart meant. And of course, I'm not sure we know all the details now, but we're a lot closer. And we'd like to try to put substance behind these pictures. This diagram in the left center is a edge replica. These are edge replicas of a sample of multiaxial laminate, which is being pulled in tension. The axis of loading, of course, is left to right. The damage developing through the thickness of these materials is clearly seen. Matrix cracking, of course, in some of the off-axis plies. As we go to the bottom right, we can see that some of these matrix cracks do indeed find each other. And by the time we get to the bottom right, there is indeed a path, a clear defect path through the thickness of these materials. And we might expect that that is the final phase of just before failure. And indeed, in some cases it is, but in other important cases, there is another feature not represented here yet. Nevertheless, we can see the failure diagram of the specimen on the right. And if we look at another sample of fatigue or solid, this is quasi-static loading of an off-axis specimen. In tension, the stress-strain curve over here on the left shows quite a lot of strain. The stress-strain curve is in blue, and you can see it goes out to almost 14% strain to break in this example. And the dielectric response to that, the polarization caused by that, when we put a plate on either side of this thing and isolate the voltage, the measured response is the red curve. Now it goes up at the beginning, okay, defects occur and they interfere with this polarization or distribution of electrons, as we said, that we expected. Then it starts down a little bit during a really long period of the life of this thing. And we might expect, okay, that's coupling. And then it goes down quite rapidly at the end. And that's a great mystery to us, and we want to look at that in several respects during the course of our discussion. Here is the experimental setup, and you can see that we have two plates on either side of the thickness of a specimen. We're placing an oscillating voltage across it. The experiment itself is shown on the right. This happens to be a glass epoxy specimen, and we're oscillating the voltage through it and measuring the cyclic response. Here's a better diagram on the left-hand side of exactly what this experiment is. Conductive plates, specimen thickness in the center. It is a dielectric, like we said, so if we oscillate the voltage, we're going to see some polarization. And where? Well, if we have defects inside, they will disrupt this alignment process through the thickness, and they will give us some sort of response. As a matter of fact, if we oscillate the voltage now, the motion of these internal electrons or whatever other polarization particles, water, for example, that's in there, will clearly tell us something is different about the path through that defect. And then, of course, on the right-hand side, during the service of this thing, if we have an applied strain or stress, we will develop defects at various places. If we have a woven material, this gets to be quite complex. And it's a great challenge for us to try to model such things. What about the theory? We won't spend a lot of time here. First of all, we don't have the time in this lecture. But most of us are familiar with Maxwell's equations and some sort of multi-physics representation of dielectric performance. And let's look at the last equation. What it says is that the divergence of this stuff inside the parentheses is 0. Well, okay, so everything inside that parenthesis must be a constant. There are only two things inside of that parenthesis. First, a subsequent set of parentheses that has sigma plus I omega, epsilon 0. Epsilon 0 is our representation of the dielectric permittivity. Sigma here is the electric conductivity, thought to be small for these materials, but sometimes not completely 0. Delta V is what change in potential as we apply our field from point to point in whatever material volume, control volume, that we're analyzing. So what does it say? It says if there's a large change in this internal parenthesis, then there's must be a large change in delta V as well, because when one goes up, the other has to go down in order to keep that product constant. So anytime we see a change through the thickness of these material properties, we're going to see a change in the potential across that material volume. Let's look at a simple experiment, which we've done in the lab, so that we know it works. And we can apply this quantity on the left-hand side, top left, is a chunk of material, could be epoxy. And in the center is something that could be the same material or something different. We'll say it's the same to start out. And on the left side of this, we put plus or minus 5 volts. On the plus side, on the right side, we put plus 5. And we go in and measure the voltage across this thing. If it's the same material, let's say epoxy all the way through, then we get a change in potential that follows this straight red curve through the center. And you would expect that the change in voltage must be uniform from point to point, since, as we saw in our expression, the material is uniform. Well, let's say that the material inside is conductive. Let's say a carbon, I don't know, chunk of carbon material, which is one of the experiments we did. Then, okay, the change, if it's conductive, then delta voltage must be less, right? Because now we have a larger term in front of that thing. So the slope must be less. It's conductive. You would expect no change, less change in voltage. If it was a copper wire, it'd be 0 change. And that's interesting. And if it's more, some material inside there that is if it's more insulative, less conductive than the center section, the slope will be greater because the change in voltage must be greater to make that thing constant if the other quantity is going down. So what happens at the interface? There is an abrupt change of voltage, rate of change of voltage across that interface, which is, by classical definition, a charge, a collection of charge, a polarization, if you will, as shown on the top right. We've done these experiments, we know it works, and so we can use this as our starting point. Well, here's an experiment that run by Fazzino, and he said, well, all right, I know where the failure is going to be if I bend this specimen until it fails in fatigue. It's going to fail in the middle of the specimen. So I can follow the failure plane as it develops through this test. We're going to run this thing until it fails, and we're going to try to follow the development of the fracture plane. That's what we're sort of focusing on here. So let's have a look at what he saw. Some of the pictures he took, again, of edge replicas during the fracture plane development are shown on the left-hand side. You can see the crack develop starting at the top tensile surface. We expected that, right? It's bending. Damage is going to start there, and it's going to progress through the thickness of this thing, a fracture plane development through the center of this sample as we cycle the specimen. So here, this is ideal. We have a fracture plane. We know it's going to go through the center. We can follow the fracture plane development, just like we said we wanted to, and see how these cracks through these different phases inside the material actually change. You can see it's a woven composite material. So he did that. And as a matter of fact, on the right-hand side, he stopped the test from time to time, put this specimens in a chamber and measured the dielectric performance. And in some cases, he introduced a material that would increase the dielectric response if it diffused into, it was an iodine material. If it diffused into that crack, it would have an even higher dielectric response than the air or moisture that might be there otherwise. So he was able to follow quite well this fracture plane development, and he got some interesting results. Let's look at the left-hand top first. This is the dielectric impedance now, the inverse of the permittivity. And this is frequency of oscillation down at the bottom. And you can see it goes from very slow, a few cycles a second, up to about 1 times 10 to E6 cycles per second. Rapid on the right, slow cycling of the voltage on the left. And he gets a really big difference in the impedance depending upon what he does. And he starts out with an undamaged material. And for low oscillation frequency, he gets quite a lot of impedance. No surprise. This is, in fact, supposed to be an insulator, or close to one. So we get a lot of impedance if we are trying to put a static current through there. But as we go to high frequency, this becomes a capacitor with some sort of dielectric in between, and the voltage is transmitted quite well by this polarization we talked about, and the magnitude goes down. Now, there's a sort of interesting way to look at those results by splitting out the real and imaginary parts of the impedance, or in this case, the real and imaginary parts of the dielectric constant. We're going to look at impedance in this case. What is the real part? Well, that's static. That's current flowing through, right? And the imaginary part, well, that's out of phase material. If the polarization is not following the change in voltage of our input, there must be some charge dissipating information as it goes through the specimen. So in the undamaged case, we get very little real transmission, but a lot of resistance, if you will, out of phase. And as I should mention, that the frequency is on this diagram, bottom left. High frequency is here close to the origin. And as we go to the right, the low frequency response is on the right-hand side. So the size of these so-called loops, these are Nyquist plots for the electrochemical people in the audience. The size of these loops tells us the amount of polarization, how much this alignment is interfering with our attempt to oscillate the voltage. You can see that undamaged, we get quite a lot. That's an enormous loop. We only get a little of it. And about 25%, you can see quite a bit of the loop. Towards the end of life, we get a very small loop, which indicates there's very little current by that time. Sort of interesting. Fazzino said, all right, I'm just going to look at the left-hand slopes of this thing. That's what this right-hand diagram is, which is a lot easier to read than what we were trying to read before. And we can see the undamaged case, just like we said, the slope is great at the undamaged situation. And as we get to this highly damaged case and finally failure, we get a curve that has very small slope. And what he did was he said, I'm going to look at that slope, quantitative impedance slope, as a function of fraction of fatigue life. So he stopped the test from time to time, broke the specimen, measured strain to break, compared that to the initial Nyquist slope, and they are quantitatively quite similar in their behavior, as you can see the top two lines. So his conclusion was, well, that's pretty interesting. There must be information here that's having a lot to do with final strength of this specimen. And looking at the diagrams we were just looking at, he concluded the following. And this is pretty similar to what we've been saying. On the left-hand side, beginning of life, no defects to interfere. And we get this Bode diagram that we looked at initially on the left-hand side of the previous slide. Function of frequency, impedance. It has this slope, goes from the top to the bottom. And there's a lot of dependence on frequency when there's a lot of polarization as the damage accumulates. But as it begins to accumulate, it begins to couple up. And by the end of life, there can actually be a conduction path between the left-hand side and the right-hand side. So then the frequency dependence is zero, as we saw. It's essentially a copper wire. There's some conductive path from left to right. Remember, he's putting in conductive material to see where that plane is going. So this conclusion of this was that the fracture plane formation is uniquely defined by dielectric behavior, and this took the silver medal in the Aeronautical Society in 2010. Well, there's one more part to this, and we have to approach it carefully. We're back to our diagram on the left-hand side, and superposed on the quasi-static loading diagram on the right are the edge replicas. And we've looked at two stages of this so far. We've looked at the loading, we get some initial defects, and then we start to see coupling when this curve bends over, and that's fine. But there's another final change in the dielectric permittivity that's very abrupt and rapid. And we want to know what that is associated with, this final diagram on the right. So we're looking at capacitance, and we see two changes, not one. It starts out, changes a little, stops going up, starts going down. And then it drops. It drops quite quickly when just before failure. Well, we are back to our discussion of dielectric relationships. And I think we can just look at the center equation, which says change in voltage at the boundary. We looked at this and measured it with our little specimen with a piece of epoxy with a piece of carbon in it. And we are able to measure the surface charge that we get when there's a change in voltage across a boundary. Now, unfortunately, sigma is the surface charge, the Maxwell-Siller's charge for the experts in the audience. So there is charge there. It's the free charge that's floating around in these materials and maybe even associated with water. But nevertheless, this charge is there. So this says change in voltage. Well, supposing I disrupt the voltage flow through the material, then I will exclude certain volumes of material from giving me a dielectric response. So I can't see this dielectric polarization if this material has been disrupted in some way to keep the signal from getting there. And that's exactly what happens. Now we're going to look at a model through the thickness, all applies model, a quasi-isotropic specimen in COMSOL, then going into, in Abacus, then going into COMSOL to predict the actual numerical values of the dielectric change. And if we start to do that, we get a very interesting response. And just a few years ago, we were completely unable to get these results. So it's thrilling for those of us who've been in this field a while. Yes, on the right-hand side, we can see for this material, regular crack spacing in the off-axis plies, predicted and observed, of course, characteristic damage spacing sometimes called, and the predicted, now these are actual predicted results. Stress strain curve is the little blue curve on the left compared to our red one we've been looking at in uniaxial tension to failure. And these codes are now able to predict the actual values of the dielectric constant that we measure in these specimens as damage develops. And they're actually able to predict the stress strain curve that we should see in the laboratory up to the point where we run out of computational power. So that looks encouraging. We also see this red stuff, and we need to talk more about what that is. And most of you have already guessed, that's delamination. We look locally where the cracks cross, the plus 45, minus 45. And by the way, we're working here at 10 hertz. So these are low frequency results. And of course, we do indeed see the delamination regions where the cracks do cross. First noticed by Highsmith, I think. And that's what we expected. They do indeed couple up with each other and combine through the thickness. But then we see a rather abrupt change to rather extensive global delamination before this thing fails and the fibers break. Now, the analysis we were looking at does predict fiber failure. So we should be able to see the fibers break in the analysis, but we are not able to predict this extensive delamination that goes all the way up the length of the sample in the specimen. And what does it do? It isolates, in these material regions, it isolates the top voltage plate from the bottom voltage plate. So the dielectric response drops rapidly because of that final event in the failure pattern. Again, here's the whole experiment laid out with the individual plies, damage in the 45s, damage in the 90s. This is off axis. And damage in the minus 45. Then there is this fracture of the 0 degree fibers predicted by the model to predict the remaining strength of this stuff at the final event. But why does the dielectric suddenly drop? Well, the lamination and isolation of some of the material from the signal, the voltage that goes through. Here is the permittivity that we're predicting as a function of strain, just like we talked about. And it goes up here without delamination. It levels off, like we said. But it doesn't drop unless we include delamination in the model. So the delamination plays a major role. And this final drop that we see in permittivity tells us that the final failure event, not only growth through the thickness, but a delamination of the sample is occurring. This is dielectric information about that. Now let's look at fatigue for a moment. And this is essentially the Navy routine. We have constant amplitude fatigue. That remains constant. We're stepping up the mean stress for this fatigue loading. Step 1, step 2, step 3, step 4. During step 4, it breaks. Not at the beginning, but towards the end of step 4, it breaks. All right, what does dielectric do? Starts out, it goes up as damage develops in step 1. Step 2 down here continues to develop. It goes up. Step 3, same story. The damage continues to develop when we increase the mean stress. Dielectric increases. But what about step 4? As the mechanical response goes up, the mean stress is raising during that period to the new level. Suddenly, the dielectric drops. And we went through the labs calling out, when it drops, it stops. So we were able to show that when this dielectric took this precipitous drop, it was a precursor or an indication to us that failure of this material was quite imminent. Now we have one more thing to do before we stop here, and that has to do with this idea of performance and data. I mentioned at the beginning that we have begun to use data-centric methods to indicate performance to satisfy certification requirements. This is the FAA requirement in our own country, and it says we can't use purely rule-based approach anymore. We have to talk about, is it going to do what we designed it to do and built the material to do or not? Now, the Europeans are even more direct. They say, all right, this is a direct statement by the European folks. We want a performance-based certification concept. Don't tell us if it's okay or not, if it's got a defect or not. Tell us if it's going to do the job we designed it to do this time. And if it isn't during the service, tell us when to stop and land the airplane or whatever else we're driving. So to do that, we need data. And maybe dielectric data is okay. The left-hand side is where we've been. The right-hand side is where we're going. We went from the rule-based certification to performance-based certification on the right-hand side. That's fine. But in order to do that, we need data. We need data coming in-service data. What is the current state of this material? And what is the current performance going to be? Is it safe or not safe? Should we take it out of service or service it? Well, to do that, we need data, and we probably need some machine that's taking the data. Maybe we don't have all the physics. Maybe we might have to learn machine learning, but of course, that's quite easy to do now because that field has developed beautifully. So some conclusions: the performance and reliability of many composite materials is defined by defect coupling and the onset of end-of-life damage, in some cases delamination, but a very abrupt disruption of material integrity. Okay, if we're going to keep track of that and certify on the basis of performance, what data do we need? And perhaps dielectric permittivity offers one answer to that question. Fail-safe and safe life certification is being replaced by this performance certification, and we have to have material state analysis, dielectric measurements enable us to get that. So our premise is that material state data, such as dielectric, should be an important part of prognosis of performance. I want to acknowledge and gratefully acknowledge the support of many organizations, NASA, for example, Department of Energy, the Heterofoam Center at the University of South Carolina, and a lot of laboratory facilities and support from the University of Texas Arlington Research Institute at Arlington, Texas. And thank you very much for your attention.
Thank you very much, Professor Reifsnider. My name is Jonathan Goodsell, and I'll be fielding questions and remind the audience to please ask questions in the Q&A box, and I will ask those then to our speaker. So let me begin. We have a couple of questions, just understanding some of the basics with the dielectric response. One question asking, are there studies that show how the stacking sequence of layers affects the dielectric response of composites? And then in a similar vein, questions about different fiber types and that response. So stacking sequence and fiber types and their influence on the dielectric response of composites.
And your first question was studies. Unfortunately, to my knowledge, there are no systematic studies of that. There are a great many studies of the constituents of different materials. Different epoxies have different dielectric constants, maybe 1, 3 something relative dielectric constant to vacuum. However, some polymer matrix materials have much higher dielectric response. You asked, the person asked, does the stacking sequence matter? Absolutely does, because they have different interfaces, different alignment of fibers, and to some extent, different materials. So anytime the material changes or the interfaces change, the stacking sequence changes, yes, it will influence the total change in dielectric permittivity through the sample. To my knowledge, and it may be out there, I have not seen a systematic study like that. I think it should be done.
Have there been studies on the differences with different fibers, glass, carbon, Kevlar, boron, or different polymers in that dielectric response?
Studies of different polymers are out there. And in fact, some of that is on the web. You can find dielectric constants of just about every common polymer used in composite materials on the web. Those are pretty well measured. The fibers I have not seen. Now the materials, glass is certainly out there. Carbon is certainly out there. Put them in the matrix and measure that at the fundamental level. Some data from University of South Carolina has been published. I'm sitting here trying to remember. I don't think anything recently has come out of there, but some of the data are there, but this is very incomplete at this point. It's a good point. We have to start with fundamental data, I think, but I should warn that when we manufacture something, starting with the constituents and estimating the properties is unacceptable from scratch. We do have to have initial readings of what the permittivity and dielectric constant is for a material as manufactured. And this group in this seminar series knows that because the manufacturer influences those answers.
And right along those lines, a question was asked about residual stresses, manufacturing-induced residual stresses, and how that plays a role and how that can be accounted for in this process, particularly in the case where different processing may lead to different levels of residual stress. How do you know your baseline, and so on?
I like the question a lot. The dielectric constant will not measure stress. It only measures strain and the deformation of the materials in the plies. To my knowledge, and I may be wrong about this, there may be a second order effect. University of Southern California had some data like that, but I have not seen convincing data that any compressive or tensile field per se changes the dielectric constant. Strain does. Stress, I don't think so. But I'm not aware of it. I think that's the clearest answer.
And following on that manufacturing theme, one of the developments currently is the idea of hybrid manufacturing processes where we mix continuous and discontinuous fibers. And a question arose around what would the effect be where you have discontinuous and perhaps even stochastically oriented fibers or even platelets within the structure. How do you account for that in this method?
Presently, I think there are two answers. I like the question a great deal because the additive manufacturing, I mean, good Lord, we're building bridges with additive manufacturing in Europe now. So that field is growing like crazy. And if we knew all of the orientations and all of the details of the internal structure, then indeed we could analytically predict those. But presently, to my knowledge, the only way is to characterize those materials once they are made to get baseline data on dielectric properties and then look for changes in those properties as a function of life, as we have done here, and look for those changes to tell us when something is ending. We're not trying to predict the absolute value of dielectric response. We're only looking at the changes in that dielectric response as a function of the history of performance of the component. So I agree, it would be terrific to have that stuff at the beginning. We don't, to my knowledge.
There are a couple of questions that maybe follow along that, and one was a question about the basic experimental setup of how do you actually go about coupling the metal plates, and is there a coupling agent? Does that have an influence? And then the second maybe scale up question, someone asked, how do you industrialize this process? How would you apply this to, say, an aircraft component or something else? So trying to understand the practical, how does one go about this?
The method itself is only a few years old. So right now, all we're doing is being careful about how the contacts are put. We saw plates which were literally clamped across the thickness. Well, I'm not going to do that on an airplane wing, but I can indeed bond, maybe with platinum paste or something, a small piece of metal on the surface of the laminate and sneak a wire out of there, just like I would a strain gauge. And at points of interest, which are defined by analysis, the stress analysis, I can make critical measurements of what I think should be the failure points. That's what's being done right now. That technology is here. The finding a tiny lead and bonding a tiny piece of metal on the surface of a sample that's carefully cleaned, of course, does give a repeatable signal and can allow us to look, for example, at a joint. I have to say the biggest interest we see right now is in using this at joints where we know there's going to be trouble. And we're trying to do that to find out if we can follow the damage development there. So, but we're using a clamp. It's not necessary. We can bond a small electrode to the surface of the material. Another related question to that is, can I get the voltage through all of these components? And so far, yes, but who knows? We've gotten up to an inch thick or so of carbon epoxy, but that's also a question that's unanswered to my knowledge.
And to follow along that, someone asked a question about non-destructive evaluation and testing, instrumentation and techniques, and how this might dovetail with that. Are there suggestions you would have for the NDE community on techniques to focus on or develop, or instrumentation to develop, that would further the application of this method and dovetail together?
I like the question a lot. We're asking ourselves that question at this point. All right, we have relationships with Lockheed, and I don't know, numerous other industries. They're asking exactly that question. Very nice. We enjoyed our visit to your lab. Now, what do we do in the field that's going to be useful? We don't have all those answers yet, but there are manufacturing methods. We're trying to work with at least one group right now. Unfortunately, it's a European group. There are manufacturing methods that might give us a way to manufacture parts that are more amenable to getting these data. We could put indeed electrodes in the manufacturing process and have a part come out, so all we need to do is bond the leads. But right now, we are in the onset of that technology, I have to say. We know it works. We don't know all the limitations yet. We hope to define those in a few years.
Let's go to some small scale questions. We've got one on understanding the measurement zone size. How small or how large can you measure, or have you measured? And then another follow-up will go to nano and the effect of what do nano layers have? What effect do nano layers have, and nanotubes and so on?
The first one is we need to, when we put a plus on one side, a minus on the other side, the voltage doesn't know where to go to get from one side to the other. It'll go everywhere within a certain volume of material. So without the modeling that we're doing, it's difficult to say, how closely should my sensors be spaced and so on. And that needs to have subsequent work. Nanomaterials, absolutely. If you have diffusion of almost anything, liquid water, for example, dielectric constant, well, could be 20. And we're looking at materials that fundamentally have dielectric constant 2 or 3. I put any moisture in there, I'm going to see it. Now, probably at the defects, which is one I want to see anyway because they're there. But absolutely any constituent, and they could be put in there for, specific reason. The folks at Nebraska are trying to do some of that. Yes, so nanomaterials could be used to enhance or to alter these signals to make them more sensitive to what it is we want to see. My answer is yes.
There have a couple of questions have come in very recently, which suggest that perhaps there's a couple of things that people are trying to make sure they understand around the influence of fabric architecture and the influence and how to deal with different fabric architectures with this method. The ability of the method to deal with alternative loadings such as shear loading as opposed to tensile loading, and finally the ability to deal with thermoplastic as opposed to thermoset composites with the rise of thermoplastics. If you might speak to the applicability across those spectra.
The thermosets, I do not have information. I would love to get, and we're actually negotiating with a company, but I would love to get more data on thermosets for this purpose. If you look at the physics, the thermoset materials should be fine. There's plenty of polarization, realignment of electrons in those materials that's available, but I do not have data for the dielectric of thermoplastic materials. I would really like to get some. I'm sorry, what was the beginning of that question?
It was looking at fabric architectures and understanding applicability across different fabric architectures, including the 3D weaves and some of the other non-wovens that are coming out.
Yeah, my question about that is, all right, I've taken data on a given material. Is that characteristic of another point in that material? And my answer is no. This method should work fine with any fiber architecture, but I do not know that the data at one point in a pristine as manufactured specimen should be the same as the data from another point. If I'm normalizing data as I go along and looking only for changes, which we've seen seem to indicate the changes in internal damage development, maybe those initial differences are not part of critical information. But I don't know that for sure at this point. We certainly do need to have more information. The fabrics in Europe that are being used, hemp, a lot of natural fabrics, they have lovely dielectric response. So I would expect this method to work with them very well. I don't actually know if that's true or not.
And perhaps a final question as we conclude here. Someone's raising the question around, at the very beginning, you introduced the idea of moving from very prescriptive rules to descriptive predictions, using models to understand what the effect of the defect would be. Someone asked the question, so what influence does that have on our safety factors, for lack of a better word? How much better are we able to, at the end of the day, how much more are we able to save? How much better are we because of these new methods?
I don't know. I like the question greatly. Safety factors, I hate to say this in public, are going out the door as far as design is concerned. Of course they will be there, and you know your boss is going to ask you what they are. I work for Pratt & Whitney, I know that's true. But they are being displaced, in this case, by risk factors. And risk is very precise. I wish we had another seminar to talk about it. So you have data here, the distribution of the specimens, the distribution of your readings, give you a way to predict risk, the chance of something happening based on, let's say, 100 data points that you have in succession. And this risk-based analysis, just on basis of probability of your measurements. And here's where AI and machine learning is beautiful, because I can get risk directly from those readings. That risk-based system is what I see out there. I haven't heard, now, okay, I don't get around as much as I might, but I haven't heard the word safety factor from an industry person in several years. This risk-based stuff really works. Statistics are beautiful. We have that stuff. We have non-precise descriptive mathematics. It's been out there a long time. Risk-based, Livermore Labs, beautiful work going on there. Risk-based is where we're going. That's what we need. We need data to do that, and machine learning will be part of that process.
Thank you very much. That is an excellent note to close here the seminar on, and thank you again, Professor Reifsnider, for your very engaging and informative seminar. This will be made available on the CDM Hub, cdmhub.org, in the next few days. And we'll thank, again, Professor Reifsnider, all the attendees. We thank the sponsors and invite you to the upcoming webinars and register at the link provided here on this page. With that, we will close today, and thank you again.